Today we are going to be starting chapter 15 on kinetics, and we're going to be focusing primarily on the rate that reactions proceed. This is a very important topic to chemistry and to other fields that use chemistry, such as environmental engineering. If you take higher level chemistry courses, you are going to be covering rates. Again, I guarantee it. And we're going to be covering it at a basic level here. Now, the first part of this section is a lot of reading, definitions, and text. So go ahead and do that. We're going to jump to the examples. Again, it feels like a waste of my time and your time to just read you what's here in front of me. You can do that at your own pace and not have to listen to somebody else try their best to read it and then you read it yourself. It's just a waste of time. But we are going to hop to the examples. Now, if you feel like you can be more productive doing the example yourself, then you can choose not to watch this lecture at all. As long as you get the content done, that's fine. However, if you feel more comfortable watching someone do it, watching the problem be solved in front of you, some people learn better that way, that's fine. This is what this video is for. And I'm going to work out examples 15.1 through 15.3, beginning with 15.1. Now, a rate, think of a rate as like this, the speed of your car. A car goes a certain number of miles per hour. It's a progression over a unit of time. And in reactions, we calculate or we consider this rate as the amount, the concentration of reactants used over a period of time. And I've written some equations up in the top corner here. I've written down the general equation that we've used a bunch, and from that, I have written our rate equation. Our rate equation is going to be the rate of the reaction is equal to K, that is our rate constant. So let me write that down. Let's say that rate is the rate of our reaction in molarity per second. Our K is the rate constant. When we calculate a rate constant for an equation for a chemical reaction, the rate constant stays the same for every time we do the reaction. The rate may change depending on what concentrations of substances and reactants we have, but the constant will always stay the same, hence the name constant. As before, anything within brackets like A or B, this is the concentration. I cannot type. Okay. And then the exponents up here, x and y, that is going to equal our order. The order is going to make more sense in a bit. We are going to do an example where we are given the order, given the concentration, and the rate, and asked to calculate the rate constant. So let's do that. That's example 15.1 on page 459 if you would like to follow along. We are given the equation 2H2 plus 2NO reacts to form 2H2O plus N2, and we are told that the reaction order of, or the order of the reactant H2 is, it's a first order reactant. Quickly, let's go ahead and establish that our H2 is the A. So everything relating to the A, such as the concentration A and and exponent x is related to the H2. So let's just say that our x is equal to 1 because we are told that the reaction below is first order with respect to H2 and second order with respect to NO. Now NO is going to be our B. B is raised to the y power. That means our NO being second order means our y will be 2. We're told that the concentration of H2, I'm going to go ahead and just write it as this, and maybe even capital MA, the concentration of A, our first reactant, is 0.012 molarity. And the concentration of our second reactant, B, is equal to 0.045 molarity. And the rate of the reaction is given. I'm going to write rate as capital R as 3.41 molarity per second. We're asked to calculate the rate constant and the overall order for the reaction. The overall order is simply the sum of all the orders of the reactants. What that means is that the overall order is going to equal x plus y, and if we have any more reactants, we could add in a z and so on, because this rate equation, we can actually expand this further if we needed to. If we had another reactant that was C, let's say C was not a product, C was a third reactant, we could have a C raised to the Z power or something like that. It can go on. But our overall order, we can go ahead and calculate. That's just going to be 2 plus 1. So our overall order for this is going to equal 3. And now to calculate K, we'll just plug in what we're given into our rate equation. What we're given is that capital R is 3.41 molarity per second. It's going to equal our unknown K value times the concentration of our A, which is 0.012. That's raised to the x power, which is 1, multiplied by our concentration of B, I think that's NO, yes it is, 0.045. Let's write in some units, molarity. The units are important to keep up with in this problem especially. This is going to be raised to the power of y, which is 2. And to solve, we're just going to divide both sides of the equation by this here. So our rate constant K is going to equal 3.41 m over s divided by 0.012 m raised to the 1 power is just itself, multiplied by 0.045 m squared. Numerically, when we work this out, we are going to get an answer of 140,000. And the units are going to be the tricky part. So let's see, we have 1 m on top, we can cross that out. We have another m on the bottom, we can cross that out. Now if we look at it on the bottom, we have an m that's squared, a concentration squared. And on the top, we have a 1 over s. So we're going to include that with our units and write it like this. You would pronounce this per molarity squared second. Anytime you have 1 over and it's part of the units, you pronounce it as per molarity squared seconds. So the answer for our rate constant K is 140,000 per molarity squared seconds. Let's do another example. I believe we're finished with that one. Yes. It's going to be a little bit different. This time we are given a reaction with 3 reactants. This reaction is first order with respect to H2O2. Let's just say that since H2O2 is our first listed reactant, that's going to be A, which means X is going to be 1, because that reactant is first order. Our second reactant is going to be I minus. We are also first order with respect to I minus. That means our second exponent, Y, is going to be 1. And we have a third exponent, or I'm sorry, a third reactant that is to the 0th order. So let's just expand this equation to include, let's just say, capital E to the X. That shouldn't be an X, that should be a Z. And it's to the 0th order. That just means the exponent is 0. We have a concentration of H2O2, which is our A. So we're going to say that MA, the concentration of A, is 0.01 molarity. We're given a concentration for I minus, that is 0.02 molarity. And we're given a concentration for H plus. I didn't write these as I meant to. This is going to be the concentration of B. And finally, a concentration of E, which is 0.0005 molarity. And we're given a rate, capital R. That rate is 2.3 times 10 to the negative 6. Now, I've written this in, I think it's called exponential form. I can't remember. It's shorthand. This E stands for times 10. So E to the negative 6 is equivalent to 10 to the negative 6. We have everything we need. Oh, this has units of M over S. Now we can plug into an equation. Probably should have distributed my values up here to give me more room to work, but that's okay. We are going to write that our rate, 2.3 e to the negative 6 molarity per second. Units are important. Make sure you keep them in. You'll see why in a bit. That's going to equal our K value multiplied by our concentration of A, 0.01 raised to the X, multiplied by our concentration of B, 0.02 raised to the X. Here I am saying units are important while not writing them. That's molarity raised to the X times 0.02 molarity raised to the X. Raised to the Y, which is 1. And then we have a concentration for H, but that's being raised to the 0 power. And remember from math that anything raised to the 0 power is just 1. So we're multiplying by 1. We don't even need to write it in technically. So we're finished. Now we just need to solve for K. K is going to equal this 2.3 e to the negative 6 m over s divided by 0.01 molarity times 0.02 molarity. One of our molarities is going to cancel out. Gosh. Which means numerically we are going to have 0.012. For units, we have an m in our denominator, and in our numerator we have a 1 over s, so we're going to write in times 1 over s. So our final answer is 0.012 per molarity second. Notice how the units of this reaction constant or rate constant are different from the previous example. That's because the order of our reaction changes our rate constant units. The units are dependent on the order of the reaction. This is just to make the units work out. But what if we aren't told the order of the reaction? We can use experimentation to discover the order for ourselves. Now, we're not actually going to conduct experiments. We're going to be, in these examples, we're going to be given the results of experiments and interpret the data to discover the reaction order of reactants and the overall reaction. There's some tables of data, which would be a lot for me to reproduce, so why don't you turn to page 462 in your book, doing example 15.2. We are given an experiment for the reaction H2 plus 2NO. I don't know what I would call this reaction. It produces N2O and H2O. It's important that he runs 3 separate trials with varying concentrations and he measures the instantaneous rate of the reaction with each of those trials. And we're given a table with the results. Notice how in trial 1 and in trial 2, the concentration of H2 was kept the same, but he changed the concentration of NO. That's important, and you'll understand why as we do the example. Also notice that for trial 1 and 3, the concentration of NO was kept the same, while the concentration of H2 was changed. Each time we had a change like this, the rate of our reaction changed. So let's write our rate equation again. And that rate is going to equal our constant K. Remember, our constant K is going to be the same for all 3 of our experiments, multiplied by the concentration of H2. This is A raised to the X power. This is one of the orders that we're trying to find. And that's going to be multiplied by the concentration of the other reactant, which is NO. This is our B. That's going to be raised to the Y power. This next thing we're going to do might look a bit weird at first, but bear with me. We are solving exponential equations, but we're doing it without using logarithms. If we were in an Algebra 2 course, we might use the logarithm function to solve for our exponents here, but we're not going to do that in this course because the math involved is simple enough to use a different method where we're only using division. So what we need to do is we are going to take 2 trials where one of the concentrations remains the same. So first, let's just take trial 1 and 2, where the concentration of H2 remains the same, and we'll plug those values in. So the rate of trial 1 was 0.00, I need to look at the screen while I write, 0.00243. This has units of molarity per second, and that's going to equal our rate constant, which is unknown at the moment, multiplied by the quantity, it's not a quantity actually, the concentration of H2, which for trial 1 was 0.3 molarity, raised to our unknown. That's going to be multiplied by the concentration of our, I think it's nitrite, which is 0.3 molarity raised to the y power. Now we will take our other equation and we're going to split it up into two parts, and we're going to use a division operation. We want to take the equation with the bigger or larger rate and put it on top. So in our case, trial number 2 has the larger instantaneous rate, so we're going to put that on top. We're going to put 0.00972 up here. That's molarity per second. And now on this side of the equation, we're going to have the same K. Our concentration of H2, which is 0.3 molarity to the x power. This time, however, our concentration of nitrite is changing. We're going to multiply that by 0.6 molarity raised to the y power. Now that we're dividing these equations by one another, we can start to cancel out some similar things. So we can cancel out these units here, the rate constant K. We can actually cancel out the entire concentration of H2. That's nice. That is going to leave us with 0.00972 divided by 0.00243. That conveniently equals exactly 4.00. And on the other side of the equation, it's going to leave us this 0.6 molarity over 0.3 molarity. Each one of those raised to the y power. Now remember, when we have a fraction where they're both raised to the same power, we can pull that power out like this, so that the whole quantity, 0.6 over 0.3, is raised to the y power. 0.6 over 0.3 is equal to 2, so we're going to rewrite this as 4.00 is equal to 2 molarity raised to the y power. And actually, no, we don't even have an m in there because these cancel out here. So we're just going to have 2 raised to the y power. We could use a logarithm to solve this, or we could just look at it. We need to ask the question, what power can we raise 2 to get 4? Well, we know that 2 squared is 4, so that means y is going to be 2. With that, we have just determined the order of our nitrite. Our nitrite has an order of 2. We can use the same procedure for finding the reactant order of our H2. This time we're going to be using trials 1 and 3, because that is when the concentration of the NO is the same. That way that one will cancel out. Let's write it over here. Since the rate of trial 3 is larger, I'm going to put that one on top. We're going to have 0.00486 molarity per second. And let's just go ahead and write it out this way. We're going to write the rates together, divided by 0.00486 243 molarity per second. And we're going to set it equal to, let's see, the concentration of H2 for, well, K. We have K on the upper and lower side. We have K in each equation. And for the trial 3, so this is trial number 3, this is trial number 1, the concentration of H2 is 0.6 raised to the x power. The units are all going to cancel out anyway, so I'm not going to write them from here on out just to save some space. This is raised to the x power, which we do not know. That's going to be multiplied by the concentration of NO, which is going to be 0.3 raised to the y power. And up on top for trial number, trial number 3 is up here. In trial number 3, we had a concentration of H2 of 0.6 raised to the x power. And in trial number 3, we had a concentration of 0.3 of our NO, and that was raised to the y power. And in trial number 1, be careful not to get your numbers mixed up because I just did. We're going to have 0.3 raised to the x power multiplied by 0.3 raised to the y power. That's the concentration of H2 to the x multiplied by the concentration of NO to the y. Now we can cross out similar terms. So the units go away, the k's go away, these both go away. That's going to leave us with this quantity, which is equal to 2. You can put this in your calculator if you want. I'm just going to write it down. Is equal to 0.6x over 0.3x to the x power, I should say. Remember, when we have 0.6 to the x over 0.3 to the x, we can rewrite this as 0.6 over 0.3 raised to the x power. 0.6 over 0.3 is 2. 2 is equal to 2 raised to the x power. And now we have to ask the question, what power are we going to raise 2 to get 2? Anything raised to the power of 1 will equal itself. So we can see with that math knowledge that our x is going to equal 1. And now we have the order of our reaction. So the overall order of the reaction is going to be 3 because that is this y term plus the x term. We can use these now with any one of the trials to calculate for our rate constant k. So let's do that. Let's pull this down. Our rate constant k. Let's use data from trial 1. The rate is going to be 0.00243. That is molarity per second. That's going to equal the rate constant k. And that's going to be multiplied by our concentration of H2, which is 0.3 m. It's going to be raised to the x power, which is 1, that we calculated. And that's multiplied by our concentration of NO, which is 0.3 m. And that's going to be raised to the second power because that's our calculated value of y. Rearranging this, we're going to have 0.00243 molarity per second over 0.3 molarity times 0.3 molarity squared. We'll cancel out the molarity on the top and bottom. That is going to give us a value of 0.09 per molarity squared second. We can plug this rate constant back into our general equation to get a standard form equation for this equation, for this chemical reaction. So plugging it in, we get that rate is equal to our calculated value, 0.09. We'll include the units per molarity squared second, and that's multiplied by the concentration of H2 to the x power, which is 1, multiplied by the concentration of NO to the y power, which is 2. Let's do example 15.3. It's a very similar process, almost the same actually. I'm going to drag over a little bit. In example 15.3, this is beginning on page 464. The data that we're going to use for our calculation is in the table. I'm not going to recreate it. We are again running 3 trials on the reaction NO2 plus CO results in NO plus CO2. We can go ahead and write the general form. That is the rate of the reaction is going to equal the reaction constant times the concentration of our first reactant, NO2, raised to the x, times the concentration of our second reactant, CO, raised to the y. And now we can use our previous method to solve for x and y and then k. So let's see, in trials 1 and 2 we have our NO2 value stays the same. So let's use trials 1 and 2 first. So let's have trial number 1 on top and trial number 2 on the bottom. It's not actually going to matter because the reaction rates are going to be the same for the 2 trials. So we're going to have 1.44 times 10 to the negative 5th for both. That's just going to cancel out to equal 1. So we can save time by just writing 1 there. And that's going to be equal to our K on both sides, multiplied by our concentration of NO2, which in our data set is 0.263. That's raised to the x power, multiplied by our concentration of CO, which is 0.826, raised to the y power. Again, I have omitted the units because they're all going to cancel out anyway. So there's no need to keep track of them in this step. They'll be important to us later. Now for the bottom half of the equation, using trial 2, the concentration of NO2 is the same, 0.263 raised to the x. However, the concentration of CO has changed. It is going to be 0.413. That's raised to the y power. And now we can start to cancel. Our K's cancel out, our NO2's cancel out. That's going to leave us with 1 is equal to 0.826 divided by 0.413 is 2 raised to the y power. If you don't see how we made that jump, just remember here these y's are going to be pulled out into one exponent at the top, and then we just divide these numbers by each other. So now we have to ask the question, what exponent can we apply to the base 2 to give us 1. Anything raised to the 0 power is equal to 1. That means our y is going to be equal to 0. Now we can run this thing again using trials 2 and 3, because in trials 2 and 3, our concentrations of CO remain the same. That'll give us another opportunity to cancel some things out. Let's write down trial number 2 and trial number 3. Our rates are going to change this time. The rate of trial number 3 is larger, so we're going to write that one on top. 5.76 times 10 to the negative fifth. I'm going to write it as e to the negative fifth. Our units are going to cancel, and that's going to equal our K multiplied by our concentration of NO2, which is 0.526 raised to the x, multiplied by our concentration of CO. I apologize for having to adjust for my little box. Maybe I can move this. I cannot. That concentration is going to be 0.413. And that's going to be raised to the y power. Now, to plug in trial number 3 data, we have a reaction rate of 1.44 e to the negative 5. And that's going to equal K times the concentration of our NO2, which is 0.263 raised to the x times 0.413 raised to the y. These cancel out, these cancel out. This quantity divided by this quantity is going to equal 4, and that's going to give us this quantity divided by this quantity is going to equal 2. Remember, our x comes out, our x combines into one exponent, and now we ask the question, what can we raise, what exponent can we apply to the base 2 to get 4? We've already done this. That answer, x is equal to 2. That means our equation, I'm going to write rate as capital R, is equal to our rate constant K multiplied by the concentration of NO2 raised to the x power multiplied by the concentration of CO raised to the 0 power. Remember, anything raised to the 0 power is 1, so we could choose to not even write it. We might write it down just to show that we have done the work. Raised to the 0 power. However, it cancels out. Doesn't matter. Now that we have this equation and the order of the equation, we can use any of our trials, let's say trial 1, to calculate for K like we have been doing. So if we understand K as equal to R over this quantity here, we're just going to go ahead and skip some steps and write K as the rate of the reaction, 1.44 e to the negative fifth. Now our units are important to us. This is going to be molarity per second. Want to make sure we get these units written down because it could trip us up if we don't. And we're going to divide it by the concentration of NO2, 0.263 m. This quantity is squared. When we work this out, we have a m squared here, so we're going to take out one of the m's here and get rid of this m here as well. This math works out to be 0.000208, and our units are per molarity second. We can use this to plug K in for this general equation, giving us that R is going to equal to this absurd quantity, 0.000208 per molarity second, times the concentration of NO2 squared. This will get you through comprehension check number 5. So do comprehension checks 1 through 5. Next week, might do a short lecture taking us to the end of the chapter, but if you want to just go ahead and do all of chapter 15 and get it over with, you're welcome to do that. I'll send the test out to you next week and you'll be finished. I'm going to be thinking of ways that we can get something equivalent to a lab final, because I know we got kind of cheated out of our labs with the coronavirus going on, but I'm going to figure something out and it's not going to hurt you. You will benefit from this in the end. So homework is comprehension checks 1 through 5. Have a good week.